I want to begin by telling you something simple, because simple things are usually the most important. Nature does not care what we intend. Nature does not care what we hope. Nature only follows her own rules. And physics, when you strip it down to its bones, is just our attempt to learn those rules by watching carefully and thinking honestly. Everything else we add on top of that, pride, fear, ambition, politics, comes later. When people hear about the atomic bomb, they often imagine it as a sudden leap in human history, as if someone woke up one morning and invented destruction. But that is not how it happened at all. The truth is much quieter and, in a strange way, much more unsettling. The bomb came from ideas that were small, gentle, and beautiful. It came from curiosity. It came from asking questions about how the world works. Long before anyone worried about explosions, physicists were puzzled by something much more innocent. We wanted to know what matter is made of. You can take a piece of chalk, break it in half, then break it again and again and again. If you keep going in your imagination, you eventually arrive at the idea that there must be some smallest pieces. We called them atoms, which originally meant uncuttable. At first, atoms were just a useful idea, a way to explain why substances behave the way they do. For a long time, atoms seemed harmless. They were tiny, invisible things that explained chemistry, heat, and gases. They rattled around, they combined, they separated. Nothing about them suggested that they were hiding an enormous secret. If anything, atoms looked boring. They were bookkeeping tools for scientists, not sources of danger. Then we learned something strange. Atoms were not solid little balls. They had parts, a nucleus at the center, heavy and dense, with lighter pieces moving around it. And when we looked closely at that nucleus, we discovered that it was held together by forces that were far stronger than anything we encountered in everyday life. The nucleus was like a tightly wound spring, squeezed by nature herself. Here is the first idea that matters. Energy is stored in structure. Whenever things are held together tightly, energy is involved. You can feel this if you stretch a rubber band. The harder it is to stretch, the more energy you store. When the band snaps back, that energy is released. The nucleus is like a rubber band stretched beyond anything you can imagine, but unlike a rubber band, it does not snap easily. Nature guards it carefully. This led us to a surprising realization. Matter itself contains energy, not chemical energy, like burning wood or gasoline, something deeper, something millions of times more powerful. The difference is not a matter of degree, it is a matter of kind. Chemical reactions rearrange atoms. Nuclear reactions rearrange the nucleus itself. That difference changes everything. Now, there is a famous relationship between mass and energy, but you do not need the formula to understand the idea. The idea is simply this. Mass is a form of energy. They are not separate things. Mass is frozen energy, trapped by the rules of nature. When the structure of a nucleus changes, a tiny amount of mass can turn into a huge amount of energy. Tiny means unimaginably small. Huge means unimaginably large. Both are true at the same time. At first, this idea felt like a curiosity, a strange feature of nature, interesting for thought experiments and calculations. No one thought about bombs. We thought about stars. We thought about why the sun shines. We thought about how the universe makes light and heat. These were peaceful questions, and the answers were beautiful. But physics has a habit of refusing to stay in the box we build for it. Once you understand how something works, you cannot pretend you do not know. And once you see that energy can be released from the nucleus, the next question is unavoidable. How fast can it happen? This is where another important idea enters, one that sounds complicated, but is actually very simple. Calculus is not about symbols and tricks. Calculus is about change. It is about how things grow, how they shrink, how fast they move, and how those rates themselves can change. If you can understand the idea of something speeding up, you already understand the heart of calculus. Imagine water dripping into a bucket, one drop at a time. Nothing exciting happens. Now imagine that the dripping speeds up. Then imagine it speeds up again. At some point, the bucket fills suddenly. The water did not appear out of nowhere. It followed simple rules, but the result feels abrupt. This is what happens when growth accelerates. In nuclear reactions, the key question is not just whether energy can be released, but whether the release can feed on itself. If one event causes two more, and each of those causes two more, you get a runaway process. This is not special to physics. You see it in population growth, in rumors, in fires. The technical name does not matter, the behavior does. In the nucleus, certain reactions can release particles that trigger more reactions. If too many of these escape, nothing dramatic happens. But if enough stay nearby, they can keep the process going. There is a tipping point. Below it, the reaction dies out. Above it, the reaction grows explosively. This tipping point is not a moral boundary, it is a physical one. The frightening thing is how little is needed once you cross that line. No complicated machinery is required to make the process violent. Nature does the work herself. All the difficulty lies in arranging the conditions just right. After that, the outcome is automatic. When physicists realized this, many of us felt a kind of unease that is hard to describe. We were not thinking about destruction yet. We were thinking about inevitability. The rules of nature had revealed a door, and once a door exists, someone will eventually walk through it. Knowledge spreads. Ideas do not stay put. Another uncomfortable truth emerged at the same time. The mathematics required to understand these processes was not exotic. It was not forbidden knowledge. It was ordinary physics, ordinary calculus, applied carefully. There was no dark equation hidden in a locked drawer. The universe was not hiding its power from us. We had simply not looked closely enough before. This is one of the reasons the story is so unsettling. We like to believe that terrible things require terrible intentions, but physics does not work that way. The same tools used to explain how a reactor produces electricity can explain how an explosion releases energy. The difference is not in the equations, it is in the context. As understanding deepened, another subtle idea became important. Nuclear reactions do not just release energy, they release it extremely fast. Chemical explosions happen quickly by human standards, but nuclear processes operate on timescales that are almost absurdly short. By the time your brain could register what is happening, it is already over. This speed magnifies everything. Speed is also where calculus quietly returns. When you ask how fast energy is released, you are asking about rates of change. When you ask whether a system remains stable or runs away, you are asking whether small changes grow or shrink over time. These are not abstract questions. They decide whether a reaction is gentle or catastrophic. At some point, the realization became unavoidable. The physics was real and it worked. Not as speculation, not as theory, but as something that could happen in the world. That moment did not arrive with fanfare. It arrived slowly, through calculations checked again and again, through experiments that confirmed what the math had suggested. I want to be very clear about something here. Physics did not suddenly become dangerous. It was always neutral. It is we who became capable of using it in dangerous ways. The laws of nature do not contain warnings. They do not say, stop here. They simply tell you what will happen if you do certain things. This leads to a deeper and more uncomfortable idea. Once knowledge exists, it cannot be undone. You cannot unlearn how nature works. You can choose not to act on that knowledge, but the knowledge remains. Someone else may act on it, perhaps with better intentions, perhaps with worse ones. Nature does not check credentials. The people who first uncovered these ideas were not villains. They were curious. They were careful. They loved understanding. Many of them were motivated by wonder, not power. This is why the story is not a simple one about good and evil. It is a story about what happens when human curiosity runs into a universe that is far more energetic than our instincts expect. There is another quiet truth hidden here. The bomb was not created by a single discovery. It was created by many small ones, each reasonable on its own. Understanding atoms, understanding nuclei, understanding energy, understanding rates of change. None of these ideas is frightening by itself. Together they form something that is. If you want to understand why this matters, think about how science progresses. We do not leap, we take steps. Each step makes sense. Each step seems harmless. But the path as a whole can lead somewhere we did not intend to go. That does not mean the steps were wrong. It means responsibility does not end with understanding. By the time the implications were fully clear, the physics could no longer be put back into the bottle. The door had been opened. Nature had answered our questions honestly, as she always does. What remained was for humans to decide what to do with the answer. This is the moment where physics and humanity collide. Physics tells you what can happen. It does not tell you what should happen. That distinction is not part of the natural world. It is something we must supply ourselves.
The unsettling part is that the universe does not slow down to give us time to think. If the conditions are right, the reaction proceeds whether we are ready or not. There is no pause button, no second thought. Once started, the process follows its course, with perfect obedience to the laws of nature. When I look back at this story, what troubles me most is not the power involved, it is the clarity. The equations were clear, the experiments were clear, the logic was clear. There was no mystery left at the end, only consequences. And so we arrive at the quiet, uncomfortable truth that sits beneath all of this. The atomic bomb was not born from madness. It was born from understanding, from learning how the universe works at a deeper level than we ever had before. The laws that govern stars also govern us. We are not separate from them. We never were. This is not a story meant to frighten you away from physics. On the contrary, understanding is the only thing that gives us a chance to act wisely. Ignorance has never protected anyone, but understanding comes with a price. Once you see how powerful nature is, you can never pretend she is gentle just because you wish her to be. That is where this part of the story must pause, not with a bang but with a realization. We asked simple questions. Nature gave us honest answers, and in those answers we found something far larger than we expected. Once the understanding was in place, the work changed its character. It was no longer about asking whether nature allowed such a process. That question had already been answered. The new question was whether it could be controlled, shaped, and made to occur under specific conditions. This is a very human question. We are always trying to take what nature offers and bend it slightly in our favor. From a physics point of view, the problem became almost mundane. If a reaction grows too slowly, nothing much happens. If it grows too fast, everything happens at once. The trick is in the balance, and balance in physics is rarely emotional. It is mathematical. It is about numbers, rates, and timing. The same calm tools used to study falling objects or vibrating strings were now being applied to something far more serious. This is where advanced calculus quietly does most of its work. Again, not as a collection of symbols, but as a way of thinking. When physicists asked how many reactions would occur in a given time, they were asking about rates. When they asked how those rates changed as conditions changed, they were asking about derivatives, whether they used that word or not. When they summed up the effects of countless tiny events, they were thinking in terms of accumulation, what mathematicians call integration. None of this felt dramatic while it was happening. Calculations were checked, then checked again. Assumptions were questioned. Approximations were improved. This is how physics always moves forward. There were no moments of thunder or revelation, just long hours of careful thought. One of the most important realizations during this period was that certainty is an illusion. Even when you understand the laws of nature very well, you never know everything. There are always uncertainties. Some come from imperfect measurements. Others come from nature herself. At very small scales, randomness is not a mistake. It is a feature. Physics does not always tell you exactly what will happen. It tells you what is likely to happen. This probabilistic character of nature plays a strange role in large events. When you have a single atom, uncertainty dominates. When you have an enormous number of atoms, patterns emerge. The randomness averages out, and behavior becomes predictable again. This is why we can build machines that work reliably, even though they are made of particles that behave unpredictably on their own. But in extreme situations, uncertainty never disappears completely. It hides in the margin. Engineers call these margins safety factors. Physicists call them error bars. Philosophers might call them humility. No matter how well you design a system, you must accept that there are things you do not know. This acceptance is uncomfortable, especially when the consequences are large. It forces you to admit that control is never absolute. You can guide nature, but you cannot command her. Once a process begins, it follows the rules you have uncovered, not the intentions you have. When everything was finally assembled, and the calculations were no longer abstract, the experience was deeply unsettling. Not because something unexpected happened, but because nothing did. Nature behaved exactly as predicted. The equations held. The models worked. This kind of success is normally the greatest pleasure a physicist can have. This time it felt different. There is a strange emotional gap between understanding something and witnessing its consequences. On paper, energy is just a number. In reality, it becomes light, heat, and force. When theory steps into the world, it loses its innocence. You can no longer pretend it is just an idea. One of the most sobering lessons here is how fast everything occurs. The timescales involved are so short that they defy intuition. Events unfold in fractions of a second that are far smaller than any human reaction time. Cause and effect blur together. By the time you could ask whether something should be happening, it already has. Physics has prepared us for this in a way. We are used to dealing with processes that happen too quickly or too slowly to observe directly. We use instruments, mathematics, and imagination to bridge the gap, but no amount of preparation fully removes the shock of seeing nature release energy on such a scale, so quickly, with such finality. Afterward, a new phase began, one that physics alone could not resolve. The questions were no longer technical, they were human. What does it mean to know how to do something like this? What responsibility comes with understanding? These are not questions that appear in textbooks, but they follow inevitably from the knowledge in those books. It is important to say clearly that physics itself does not answer moral questions. If you ask nature whether something is right or wrong, she remains silent. She will tell you what will happen if you arrange the conditions a certain way. She will not tell you whether you should arrange them at all. This silence can be disturbing. We often hope that deep knowledge will come with deep guidance, but the universe does not work that way. Wisdom is not built into the laws of motion or energy. It must come from somewhere else. One of the hardest things for scientists to accept is that understanding gives power, but not direction. You can learn how to harness enormous forces without learning when to stop. The skills required to calculate an outcome are not the same as the skills required to judge its value. There is another uncomfortable truth hidden in all this. Once a method is known, it does not remain unique. Knowledge spreads, techniques improve. What begins as a singular achievement becomes, over time, a general capability. This is how science advances, but it is also how dangers multiply. You might hope that secrecy could solve this problem, that knowledge could be locked away. History suggests otherwise. Secrets slow things down, but they do not stop them. If something is allowed by nature, and understandable by the human mind, it will eventually be rediscovered. This is why the real challenge is not whether we can prevent knowledge from existing, but whether we can learn to live responsibly with it. That is not a scientific problem. It is a social one. It involves trust, communication, and restraint, qualities that do not come naturally to large groups of people. From a physicist's perspective, there is a temptation to retreat into the comfort of equations. Numbers are honest. They do not argue. They do not deceive themselves. But the world those numbers describe is inhabited by people, and people are complicated. In thinking about all this, I am often reminded that science is a human activity. It is done by people, with hopes, fears, and limitations. The idea that scientists are detached or cold is a misunderstanding. The emotional weight of understanding something powerful can be enormous. At the same time, abandoning curiosity is not an option. Curiosity is not a luxury. It is part of what makes us human. To stop asking questions because the answers might be dangerous would freeze us in place. Progress would halt, but danger would not disappear. The challenge then is balance. We must learn as much as we can about the world, while also learning how to live with what we discover. This requires education that goes beyond fact. It requires teaching people how to think, how to doubt, and how to take responsibility for the consequences of their actions. Physics can help with part of this. It teaches humility. It shows us how small we are compared to the forces of nature. It reminds us that the universe is not built for our convenience. These lessons are valuable, even outside the laboratory. One of the most important habits physics encourages is honesty. You must follow the evidence wherever it leads, even if you do not like the result. You must admit when you are wrong. You must accept uncertainty. These habits are just as important in society as they are in science. When people ask whether the atomic age changed physics, the answer is no. The laws remained the same. What changed was our relationship to those laws. We crossed a threshold of capability, and with it came a new level of responsibility. This responsibility does not belong to scientists alone. Once knowledge enters the world, it becomes part of human culture. Decisions about how it is used involve everyone, directly or indirectly. Pretending otherwise is a way of avoiding hard questions. If there is any comfort to be found, it is in the fact that understanding also gives us tools to prevent disaster. The same physics that explains explosive reactions also explains how to control them. The same mathematics that predicts runaway growth can predict stability. Knowledge cuts both ways, but control is never perfect. It requires constant attention. Systems drift, conditions change, complacency grows. Physics does not forgive carelessness. It waits patiently for mistakes. This is why the story does not end with a single event. It continues as long as we continue to understand the world. At a deep level, each new insight carries potential, both creative and destructive. The question is not whether this will happen, but how we will respond. I do not believe that the lesson here is despair. It is seriousness. The universe is not malicious, but it is powerful. Treating it lightly is a mistake. Treating knowledge lightly is an even greater one. In the end, the most unsettling realization is also the simplest. The same mind that can uncover the deepest secrets of nature must also decide how to live with them. There is no external authority to appeal to, no cosmic judge to consult. The responsibility rests with us. Physics can tell you how stars burn, how atoms bind, how energy flows. It can show you the structure beneath appearances. What it cannot do is tell you what kind of world you want to build with that knowledge. That choice remains open. It always will, and that perhaps is the most important thing to understand.